All right, everyone. We are going to continue with forces this week. Right, last week we learned about the types of forces. We're going to expand on that. We're going to start with the second part, which is drawing force arrow diagrams. So, first thing is make sure that you have your digital notebook open. You have another table set up, ready to go to take notes, right? And again, as always, anytime that there's pictures or drawings or anything that I write on there or type in there, those should all be included in the notes. All right, so let's get started. All right, so in the types of forces lab that you did, you started to draw some force arrow diagrams, right? Now what we're going to do is we're going to add in the idea that the arrow length really, really matters, right? In the types of forces lab, I just said, hey, let's make sure that you're just drawing them in the right direction, all right? So when we draw force arrow diagrams, an arrow is really, really great because, again, right, a force is strength and direction, right? And an arrow does both. And the way the arrow does both is, number one, it shows us which direction it's going because we can point that arrow right, left, up, down, right? And it also tells us how strong it is because we can make the arrow longer or shorter to show that it was a really, really strong force or it was a really, really weak force. Right, so it's really, really important that when you are drawing your force arrow diagrams in the future, right, we really, really need to make sure that when we draw those arrows, we have to compare that to what were the other arrows. So if we say one force is stronger than the other, we need to make sure we draw that arrow much longer than the other one. So in this case, right, if these two arrows are side by side, I can clearly show that this arrow is probably twice as long as this one. So what you're really saying is this force is stronger than this force 2 times stronger. Okay, so that's kind of like just a brief description a little bit about how to draw arrows on a force arrow diagram. All right, so now let's get into the specifics. All right, so when we start talking about drawing force arrow diagrams, what we want to really, really start focusing on is, are the forces balanced or are they unbalanced in regards to each situation? All right, and understanding that if something is balanced or unbalanced dictates what kind of motion is it having, right? Up until this point, we've been talking about, right, how to calculate speeds and stuff like that. Well, now what we're talking about is how do forces affect speed, right? Affect acceleration. So the first thing we're going to look at is balanced forces, right? Just the idea what it sounds like, it's balanced. What that means is all the forces that are affecting that object are equal to each other, right? So if you look at this force arrow diagram here, you can clearly see that the force is going in the right direction, right? This one right here is equal to that of the one that's pushing it or pulling it in the left direction. When that happens, we can say that the forces are balanced. Now, what does that mean for an object that is for an object's motion? Well, what we can say is that there's going to be no change in motion, or we can say that there's no acceleration that's going to happen when the forces are balanced. Okay, this is a really, really big, important part as we move forward, understanding that, hey, if things are equal, nothing is going to change. The object is going to continue doing exactly what it was doing before. So if it was staying still, it's going to stay still. If it was moving at 30 miles per hour, it's going to continue moving at 30 miles per hour until those forces get unbalanced. And we'll talk about that in a minute. All right, so here are some examples that you might see with balanced forces. So the first one is kind of like tug of war, right? If we have two teams that are neck and neck and they're pulling and they're not moving at all, right? Now there's forces that are happening, right? Each of those people are pulling as hard as they could with all their might, but they're not moving, right? Well, why is it that they're not moving or they're not accelerating? And that's because both sides are pulling with equal amounts of force. So you can have it where, right, balanced forces creates no movement whatsoever. The other one, and this is a tricky one because you're thinking, okay, the object is moving, so wouldn't that mean one of the forces is winning? Not true, right? So if we look at little Wile E. Coyote here that's parachuting down, if an object is moving at a constant speed, right, that means, right, we've learned in the past that constant speed means no acceleration, right? What that means is if an object is moving at the exact same speed the entire time, that also means that all the forces that are affecting it are equal, are balanced with one another. And that's the reason why they're not accelerating. So here's just two examples of balanced forces. One is nothing is moving, and the other one is, yeah, it could still be moving, it's just moving at a constant speed or no acceleration. All right, so now what happens when the forces are unbalanced, right? So we've already talked about what happens when things stay balanced. So when things are unbalanced, now we're going to get that change, right? We're going to get a change in motion. So what does that change in motion look like? Well, there's going to be some kind of acceleration that occurs, right? And that means, remember, acceleration could be speeding up, the object is going to slow down, or it's going to change direction, right? It's going to do one of those three things whenever forces are unbalanced, right? And here's the thing. You're always going to have multiple forces around. There's never a time where just one force is affecting one object. There's always going to be multiple, right? And so what we are always looking at is, hey, if you say, ooh, that thing is getting faster, what that means is that object has unbalanced forces somewhere. One of the forces has to be stronger than the other, right? So what does that mean when you're drawing force arrow diagrams? Well, that means that number one, we need to make sure that we draw the arrow that's stronger, right? Or the force that's stronger, we got to make that arrow longer. So in this case, right, if this is 150 newtons of strength, of force, we need to make sure that this arrow is much, much longer than the 40 Newton one that's over here, right? Almost like 4 times longer than this one. Okay, so that's how we kind of show unbalanced forces. It's very different from the one that we showed with balanced forces. But really, the key part that I really want you to focus on is if there's any unbalanced forces, there has to be some kind of accelerating that's happening. Let's look at some examples of unbalanced forces, right? So I gave you two right here. One is a car speeding up, right? Again, there's acceleration that's taking place. So if a car is speeding up, what is it doing? It's getting faster and faster and faster and faster. Well, that means that the force that's making it go forward has to be stronger than any force that's pushing against it, okay? And then if you look at the girl in the shopping cart, this is great, right? Well, what happens to her when she hits the wall, right? She comes to a complete stop. Well, in order to come to a complete stop, it has to slow down, and it slows down very, very suddenly. So we know that the force that's pushing against her, right, against the shopping cart, is going to be much, much more unbalanced than the force that it took for her to go straight forward. So these are just some examples of what happens to an object, right, when we have unbalanced forces. We got something that speeds up, right, or we have something that really, really slows down and comes, in this case, to a complete stop. So just like when we're talking about calculating speed and stuff like that, one of the things, again, with science, what we do is we want to quantify, right? We want to give numbers as to how do we know if something is balanced or unbalanced, right? And if it is unbalanced, how strongly is it unbalanced? It's one thing to say, oh yeah, it's unbalanced. Well, a lot of times we want to say, well, how much, right? So one of the way we do that is by what's called calculating the net force. And the net force really just means is we take all the forces that are affecting it and we put them all together, right? And so when we put them together, we're adding and we're subtracting, just like we would do it obviously in math class. So what we need to figure out is when do we add and when do we subtract, right, in this place. So I have a force arrow diagram right here. And so what we're going to do is, as you can see, the equation for net force, and sometimes I'll write net force as NF because I don't want to write the whole thing out, right? What you do is you take all the forces on one side. So in this case, right, I've got one that's, and when I say sides, what I'm really talking about is which direction are the forces going, right? Because in other words, I can move this arrow over here, right? But in reality, right, it's still pointing to the left, right, instead of pointing to the right. So I want to make sure that I'm looking at which arrows are pointing in which direction, really, I should say. All right, so in this case, I'm going to look at the directions that are pointing to the right. Okay, so that one is 35 newtons large. So what I'm going to do is I'm going to say, all right, I have 35 newtons. Okay, and I'm going to subtract that, and there's no other arrow going right. So I know that there's only one force going in the right direction. Okay, now I look over here and I see that there's two forces going in the left direction, right? Now, when I see two arrows going in the same direction, what I want to do is I want to add those up, because what I'm saying is yes, there are two different forces affecting the object, but since both of those forces are going in the same direction, it's going to be pushing, right, in the left way, both. So really, like, I'm kind of doing this, right? If I wanted to put it together, I'm kind of making like an arrow that's like something like sort of like this, right? I can add them together. So what I'm going to do is I'm going to go, okay, well, I'm going to go 15 newtons, right, plus 15 newtons here. Now, I haven't talked about the minus sign yet. Why did I put a minus sign here in a minute? Okay. Now, the reason why I'm putting a minus sign between the 35 newtons and the 215 newtons that I've added together here is because they're going in the opposite direction, right? And so when they're going in the opposite direction, they're going to start canceling each other out. It's just like when you're doing tug of war, or if you're trying to push a box, right, and the other person's trying to push a box towards you. You guys are both, right, trying to push hard, but there's always going to be one person maybe that's a little bit stronger than the other. So in this case, it's like, hey, which one's stronger? Well, in this case, right, if I add these up, 15 plus 15 is 30, and I'm going to subtract that by 35. So 35 minus 30. So in reality, I know that I have 5 newtons of net force. Now, I want to also make sure that I have to do one other thing. Remember, force tells us what? It tells us how strong it is, which is the 5 newtons, and it also has to tell me what direction it's going, okay? So in this case, it is going to the right because the right force is much, or not much, it's just a little bit stronger than the both arrows going to the left. So in this case, my net force would be 5 newtons to the right. And that's how I would write it, and that's how I should have highlighted the whole thing. Sorry. All right, so I want to be able to say my answer is net force equals 5 newtons to the right. So when I put all these forces together, it's really, really functioning. This object is functioning as if there was only one force pushing it to the right, okay? And that's how we would calculate net force. Let's put everything together that we've learned for this kind of set of notes for this one. Now you're going to notice that this one's a little bit different because now I'm introducing an up and down arrows. Right? So I'll talk a little bit in a minute about what to do when you have that happening, right? But first, what we want to do is we want to look through this and say, okay, is this object balanced? Are the forces balanced or unbalanced? And a lot of times, right, even without calculating the net force, we can kind of sit there and go, if you look at the picture, you can clearly see that the forces are unbalanced, right? Just because, number one, this arrow is much, much longer than this arrow, okay? So in order for their unbalanced, for something to be balanced or unbalanced, everything has to be unbalanced, right? The entire problem has to be 0 newtons, right, in order for it to be unbalanced. So in this case, we know that it's unbalanced, right? So I'm going to move over and say this is an unbalanced situation here. So I know, right, that if it's unbalanced, well, what's going to happen to my object? Well, guess what? It's going to accelerate, right? So there's going to be a change in motion, right? At this point, we don't know because we don't know which way the object is moving and stuff. We don't know if it's going to speed up, if it's going to slow down, or if it's going to change directions. But what we do know is it's going to accelerate, right? I need a little bit more information to know if it's speeding up or all that kind of stuff. But it's going to accelerate in some form. Remember, acceleration is it speeds up, slows down, or changes direction. It's going to do one of those things, okay? So now what we need to do is, in order to answer the last question, which way will the object move, we kind of have to find the net force, right? Because we need to know kind of like which kind of what's going to happen here. So in this case, and I'm just going to kind of move everything over. Oops. All right, I've already kind of like made my calculations. I just didn't want to type and explain everything at the same time. So here's one of the things: when you have up, down, left, right arrows, it's actually 2 problems in one. All right. The way I have to treat this is I have to treat each plane separately. In other words, I have to treat the left-right arrows separately from the up-down arrows because I can't add and subtract arrows that are not going like against each other or with each other. Okay? So in the first case, what I'm going to do is if you look at the first line, I'm going to just take the left and the right forces, right? So in this case, I'm taking 65 newtons minus the 20 newtons because again, right, those 2 forces are going against each other. So I'm going to subtract, right? If they were going with each other, I would add. But since they're going against each other, I'm going to go, right? I'm going to subtract. So that's the reason why it's 65 minus 20. So I get 45 newtons to the right, right? Because again, my right arrow is much stronger than my left arrow, right? Remember, it's the right arrow. When I say right arrow, it means the direction that it's pointing, right? Now I'm going to look at my down and up arrows. So in this case, I have my 20 newtons, right? And I have 10 newtons. They're going again in the different direction. So since they're going in different directions, I'm going to subtract those two forces, right? I have to calculate the net of those two. So 20 minus 10 is 10 newtons. And again, I have to write the direction down. So in this case, right, my down arrow is stronger than my up arrow. So I know that the object, right, is going to be going downwards. All right, so it's 10 newtons down. So my answer is not just, I can't add or subtract these two numbers together because it's again, I can't subtract left, rights from the up and downs. So my answer is net force equals 45 newtons right and 10 newtons downwards. All right, so that's my answer. So it's kind of like a two-part answer to it. At this point, when it says which way would the object move, well, the direction tells you it's going to move right and down, especially if the object was moving or staying still. It's now going to move kind of like right and down this way. It's going to move at a diagonal to the right as we're going through it. So this object, it would go like kind of like that, okay, as it's going through. So that's how we would put together, anytime that we're doing force arrow diagrams, these are the 4 questions I'm going to ask, all right, as you're going through it. All right, and that's our set of notes for this week.